So welcome to the presentation about the TestStandifier. TestStandifier actually is a tool that we made to adapt a DQMH module to be used into testing. If you have questions, raise your hands and wait for the microphone so that we can all hear your question, and questions will be recorded also. Question can arise at the end of the presentation or during the presentation, so if you have a quick question, feel free to interrupt when you want. So, quick note about myself. I'm Cyril Gambini. I work at Neosoft Technologies. I'm a CLA, CTA, and also LabVIEW champion. 18 years working with an AI product, mainly LabVIEW, but also a lot of TestStand, VeriStand, a little bit of FlexLogger when I'm forced to. 17 years working for AI partners. So mainly my job is to work on customer project. In these 17 years, I can't say I've never worked on similar project. Each time is a new project, new solution. Pretty interesting job, actually. And I'm currently the Vice President of Engineering at Neosoft Technology, so we are based in Canada. You might know my name, maybe because I'm involved in several open source projects. You might know Antidoc, for example, that you use in your DQMH, with your DQMH developments. Antidoc is, I did not create Antidoc, but actually I created the libraries that makes a graph view into Antidoc. Neosoft Technologies, we were founded in 2000. Our nine partners since 2008. We've got a bunch of very good and certified employees, CLA, CLD, CTA, GLAD, etc. We are also DQMH trusted advisors, which means that we have an extensive knowledge of DQMH and how to use DQMH in your application. It may be on a Windows PC or to target executable, standard executable, or in TestStand. Basically, at Neosoft Technologies, we are a company where we create software, custom software for measurement and test system. We have extensive knowledge working with Compact Reader, for example, or PXI chassis and PXI systems. We do software and hardware in the loop systems, and we also work a little bit in vision. So if you have vision projects, we'll be happy to talk about it. The agenda will be quite simple. I will just try to present a little bit again what is DQMH and what is TestStand, and we will see some strong points in key ideas of what is a module, DQMH module, and what is TestStand or how TestStand is actually behaving, and then we will see how to integrate a DQMH module into TestStand, and what led to the tools I'm presenting actually today, which is the TestStandifier. You would say that TestStandifier is creating what we call an output that you will be using into TestStand. So I will present what is actually created by the TestStandifier and how to use it. Before diving into the technique, here's our ephemeral giant slide. I would just want to, maybe you know Barbara Liskov already, but I'm pretty sure you know at least the principle of Liskov substitution. If you do a lot of OOP, actually, second woman to receive Turing Award, pretty amazing woman, currently professor at the MIT. So yeah, pretty amazing career. But before, question.
Are we going to be able to get the slides?
Will we be able to get the slides or for your presentation?
I will actually try to make them available online. Yes. Just before diving into the technique, I just want to make a quick poll. How many of you is already using DQMH? Quite a lot, not everyone. Okay, and same thing for TestStand? Yeah, okay, good. If you have specific question about DQMH, or if you have specific question on TestStand, and concept that we'll just talk about in a minute, feel free to interrupt, and I will maybe try to clarify, but in the slides, I assume that you have knowledge or of DQMH or of TestStand or of both, actually. Just a quick recap. What is TestStand? TestStand, actually, it's an engine. So to run test sequences that you will create, and all along your sequence, you will call adapters to actually execute code that is made in LabVIEW. Could be .NET assembly, DLL, whatever. And on top of TestStand, we've got UIs that allow to create a sequence or visualize actually your sequence. So what we see actually here, often we call that TestStand, but this is not TestStand. This is a sequence editor. This is a UI, which is quite different. So TestStand is the engine. And what is DQMH? So several DQMH users here, but DQMH stands for Delacroix Queued Message Handler. It's actually a framework that is freely available, and you can download it from VIPM. And you can use DQMH in many applications, from RT to Windows systems. And I've got a few points here. The third one is modules are executing as long as needed. And why I've got this here, you will see that in a few slides after, but actually you must understand that a module is actually running and don't stop running until we say so. Okay, it doesn't have a lifespan, so the execution of a module can be as long as you decide it to be. In a DQMH module, we've got a public API, so it's all the requests that you can create from the testers, and the public API is what a user is going to use to actually interact with the main module core. And the tester is something that is created each time you create a new request or a new broadcast. So a tester is a VI that is running on the side and that can capture broadcasts or from which you can manually trigger requests and get reply. DQMH framework is maintained by a consortium, so it's 5 person running their own business, and actually part of the DQMH modules are all using DQMH in their own business, and they maintain it. And so it makes me confident that DQMH is not close to disappear, and it's very high quality. So, what is the purpose of using TestStand? We use TestStand to execute scripted sequences, give a status to UT, report results, etc. So a lot of things that are already included into TestStand that you might be using already. Actually, TestStand handles when a code is executed. When I teach TestStand, I often say, find out when a code should be executed, and you will know where to add your code into your sequence or into your process model. And TestStand can handle one UT or multiple UT. So you have batch or parallel process model, actually. And the TestStand engine will actually duplicate everything for you, all the sequence and the executions. So you can imagine that you have one sequence, but 16 UT, you will have 16 actually sequence running. And the TestStand will duplicate that one sequence into 16. DQMH modules can be singletons or clonables. This is to make a parallel to the number of UUTs that you can actually handle with TestStand. So one UUT can think of singleton, for example. Maybe not true, but this is something that we can think of. Multiple UUTs, clonables. You know that the tester is built for free and very useful, and this is something that maybe we will see that we can use from TestStand. And it also enforces documentation. So if you document correctly your module, you will have free documentation at the end using something like NTDoc, for example. So help to actually document your code. And you need to control when to start and stop a module. And one of the great things is that you can keep data into the data context of your DQMH module. So DQMH module is somehow also a memory. You can see DQMH module as a memory. So before diving into using DQMH with TestStand, I just want to make a quick recap of what is traditional TestStand programming. So if you are TestStand programmers, most of the time what we do is that we've got a single VI, that we make it a step out of it, and your single VI will actually perform something, calculation, acquisition, something like this. It will give an output, TestStand will get the output and go to the next step. What we try to do is to make step to be short in time. Okay, when an adapter runs, so if you have LabVIEW code, the LabVIEW TestStand will actually run the LabVIEW code through an adapter, so it will give the hand to the LabVIEW runtime engine to actually run the VI. While the adapter runs, TestStand waits. So this is a crucial point, actually. So if your step has a duration of 3 hours, TestStand will just wait for 3 hours until the step actually returns. So if your step is not short in time, you need to handle termination within the step. So this is what we see actually here. We've got an execution monitor VI that is actually monitoring if an operator, for example, press on the step button of your TestStand application, your UI, and to actually stop the loop. A step also might produce error, and if a step produces error, so TestStand can catch the error, and most of the time you can actually add a runtime error callback into your sequence and handle the error inside your sequence. And so step may produce data for result processing and reporting, of course. In traditional TestStand programming, if you want to actually stop at a certain point in your sequence and see what your VI will do, you just add a breakpoint in your sequence in front of your step. Go to the breakpoint, press F8, and you dive into your step, and you actually see what the step is doing, right? This is a crucial point because it will not work that way with DQMH. So just keep that in mind. Last thing also is that maybe that VI, that small VI that we see here, when we tested it, we only tested it with that DQMH task we see here. It was working well, no problem. But at the moment you move your VI into your sequence, you have to add that monitoring, execution monitoring VI. So you need to modify actually your IP to integrate some more functionalities related to TestStand and not related to your test itself. So sometimes when you have a LabVIEW VI that works and it's all tracked thanks to your SCC, maybe you're using Git or SVN, you will see that you will need to modify your VI and you will have to track that modification just because you will be using it into testing. So the question is, why using DQMH with TestStand? Now, more than 15 years that I'm doing testing. DQMH is not 15 years old. I'm doing testing without DQMH for years. Why should I change that? It was better before. You always heard that already, I'm sure. Actually, there are several reasons why you want to use DQMH with testing. You can actually develop your module without testing in mind. So your module is autonomous. You provide a public API. You've got a tester. You can all test your IP or module thanks to the tester. And you benefit of all the good stuff that you have with DQMH, like the possibility to create helper loops. You can do continuous monitoring into your helper loop. So there are many reasons why you want to use actually DQMH with testing. And also, as I said before, one of the default templates that you have with the DQMH is that you can make a module to be clonable, and so that will fit well with batch and parallel process model. So if you have, for example, 16 multimeter, which is not what you will have, I hope, but you may create one DQMH module to control a DMM, but you have 16 sockets, and you will just clone 16 times your DQMH module, and you will be able to control independently each DMM thanks to the same module. So we see that there are a lot of benefits actually of using DQMH with testing. But is it as easy as it seems to be? When we first used DQMH with testing, I must say I went through the DQMH examples, and there are a few examples that are delivered with DQMH to actually use a module into testing. And if you look at the examples, actually, they are made just like as you would do with traditional testing programming. So if you start your sequence, for example, you will need to do special things to launch your module. You will have to think about it. You have several steps actually to launch a module. You need to start a module and synchronize it. How you do this into testing. There are clever ways to do it. What happens if you need to rapidly stop your sequence execution? We'll see that there is a small problem actually when you are using request and reply, because this is what you will use actually most of the time in your sequence, is that you ask a question to your module, so you request something, and you will wait for the module to actually answer to your request. While it's waiting, I don't know if you dived into the code of a request and reply VI, but the wait is actually a notifier, and so the wait is a timeout of the notifier. Notifier is the LabVIEW primitive. You cannot stop it. By default, you've got a timeout of 5 seconds, which now you can change it. But if you send a request to your DQMH module, and for any reason the module doesn't respond, the sequence will be stuck waiting for the answer or for the timeout for 5 seconds. 5 seconds can be quite long if the test bench is in fire. So we may need to find a way to rapidly stop the sequence when the user needs it. Also, for all the DQMH users out there, you know that into a DQMH module, by default, into your MHL, you've got a case that is named error. So by default, the DQMH module is doing error handling that you can customize, but there is error handling into your module. But there is also error handling in testing, actually. Where should you do your error handling? Into your DQMH module, into testing? You will have to think about it. Also, one of the benefits of using DQMH is to use a tester. So for all the DQMH users, we know that the tester is a very crucial part of using DQMH. But the tester actually allows you to see what's going on into your main VI. The main VI is hidden. It's running in the background in parallel to your sequence. So the tester is like a window of what's going on inside your module. But the tester, it's a while loop actually. So if you call the tester from TestStand, it will never returns until you stop the tester. But if you stop the tester, you lose your window onto your main VI. So tester is blocking execution. So we'll have to find a way to actually make it a non-blocking VI. And something that is a little bit more complicated, but if you are using clonable modules in DQMH, you have a module ID. So a module ID allows you to target a specific clone that is running. Most of the time, what we want to do is we want to synchronize the module ID on the test socket index. Test socket index is a variable that is populated by TestStand. And so the number that you have into that variables is a number of your socket. So most of the time, you will want to synchronize your test socket index with your module ID. But the module ID into a clonable module is generated from a feedback node, so from a memory. And if you execute TestStand with multiple UTs, you will see that and launch a new clonable module each time your socket is running. You will see that between execution, TestStand may or may not empty its cache. And what will happen next time you will run your sequence, the module ID will just increment. And so you will lose the synchronization between your module ID and your test socket index. What may happen also is that you have a batch module or parallel module, for example, with 8 UTs. TestStand will actually start the sockets one after the other, but they will start executing not in the same order. So maybe the first socket will start, but then the third socket will start, and then the fifth one. But if the fifth one is third, maybe its module ID will be 3 instead of 5. So you will have a desynchronization between your test socket index and your module ID. So you will have to find a way to actually synchronize which socket is talking to which module. And if your module is actually talking to hardware, here the problems come. You might be not talking to the good piece of hardware for your specific test socket. So all that are the problems we try to fix with a TestStandifier. So the TestStandifier, just to I'll give a quick story of it. It's what I call a Netflix idea. So it's a Saturday evening, looking at Netflix, not enjoying the show, and an idea pops up. And hey, if I do something that can automate all the changes that is required into a module to make it faster, actually, and so that I can have a program and link that for me. And like all Netflix ideas, they seem easy on the couch, but when you start working on it, it's not that easy anymore. So I will try to go through the slide and give the recipe of what we are trying to do into the TestStandifier and why it solves the problems I exposed in the previous slide. In the TestStandifier, the first thing we do is validating a module. To do this, we rely on the DQMH validator. So I don't know if the DQMH users here know about the validator, but the validator is a tool that you can trigger from the DQMH menu that will scan a module and ensure that everything in your module complies actually with DQMH paradigm. If the DQMH validator finds something that you modified and you shouldn't have to, it will raise an error, and we will stop the TestStandifier process. a modified module might run well on your system, on your computer, but it may break all the modifications that we are doing afterwards, because it's all done with VI scripting, and so we should be able to find all the different markers that you will find to your DQMH modules. And you can't imagine how many weird stuff we saw. So the first version of the TestStandifier was given to one of the other DQMH trusted advisor we know, wired in Australia. And Stuart, who is an employee wired in, told me, hey, I've got some errors with your tool. Okay, let's dive into it. Its module was crazy. The tester was in the library. Some DQMH tags were removed. No more error in the MHL case. Many things going on. And so the first version was tested on bright, new, stock DQMH modules. Was running well, but as soon as you have DQMH modules that was customized a little, it was breaking everything. So instead of trying to patch every situation and find out how we can deal with that, we actually decided to go through the validation. If your module is valid from the DQMH point of view, we can work on it. If it's not, we will just stop and you will have to fix whatever happens in your module. Then we create a source distribution. We'll do more than that, but this is actually the first step. Why do we create a source distribution? The main reason is that we never want to touch your original module. If you remember the slide on traditional test and programming, you have a VI, and just because you are using it into your test and sequence, you may need to add some more VIs, or you need to modify your existing IP that was maybe tested. And so you have a change in your SCC, for example. So we don't want to do this on the original module. So you keep your DQMH module as it is, and we create a source attribution just to duplicate it. And we'll relink all the sub-VIs to be flattened, and the new DQMH modules that we create thanks to the source distribution is all self-dependent, which is very important for a second thing that we are doing after. And we modify slightly the module in the source distribution output. So we insert the tester into the library, and we create wrappers on top of it. These wrappers will allow after to run the tester in a parallel execution and to remove the fact that the tester is a blocking loop. We also modify requests and replies, and I will show you that right after, just to try to stop or to be able to stop actually the execution rapidly. And we also modify from the source distribution the way that the module ID is handled into clonable modules. So it will be easier for you to synchronize the module ID thanks to the test socket index afterwards. The main idea here behind the source distribution is that we never ever to touch your original module. So if you use that DQMH module into another application, for example, it will not be changed. So here is one of the modifications we do, for example, automatically for all requests and replies into your module. So, and just to make a small parallel with the validation, we have to find all the requests and replies actually into the targeted module. So for that, we use specific keys that are added into DQMH when you create a request and reply. So if you modify your DQMH module, if you modify the ways that the DQMH scripters created your request and reply, this may not work. So validation will ensure that your request and reply is actually valid and we can modify it. So here we see that the DQMH waiting for an answer, is actually a primitive. So as soon as we enter into the wait for the notification, it will just wait until it receives actually the notification or the timeout. In some modules, dealing with hardware that are pretty slow, we've seen timeouts to be close to 30 seconds, some more, even more, several minutes. But you understand if you call that request and reply in TestStand, and the hardware actually does not answer, you will have to wait until the timeout is reached, actually. So what we do automatically, we find that timeout VI constant, and we had what we have here is simply a VI that divides the timeout into a 100 milliseconds chunks. So now we just loop around the DQMH wait in chunks of 100 milliseconds. And we add automatically the TestStand monitoring surveillance. So if a user actually presses on the stop button to stop the sequence, we should not wait more than 100 milliseconds to actually stop the sequence and go out of the waiting. So here, if you look at the TestStand and DQMH examples that are already shipped with your DQMH module, they do exactly the same thing, but inside the main VI. So in the examples, the monitoring, the stop for monitoring the termination, is done into the main VI. So each time you've got an MHL case, they were also monitoring the execution of TestStand. But it means that you are modifying an IP that was already validated before. So you change the main VI, which I do not want to. We know that your module is working, you've tested it, and you decided to use it into TestStand. I don't want to change the main VI, which is the core of your DQMH module. So instead, we change the way the request and reply is actually handled. Another thing that we do is that we make the DQMH tester to be runnable in parallel to your sequence. By default, I said it before, but the tester is a while loop, actually. So if you launch a tester, it will wait until you actually close the window. So to stop a tester, you have to close the window. So what we do is we modify it slightly the way, so we create a specific wrapper, actually, to programmatically launch your tester in a parallel execution. And so that to launch the tester, it will run in parallel to your sequence. So you will still have the while loop, but your sequence will be able to continue right after that. But we had to find a way to close the tester also, because you might want to close the tester at the end of your sequence execution. And this was a tricky one, because there is no API to actually close a tester. So we asked the DQMH consortium, is it possible to add an API just to close the tester? The answer was no. This is not a typical use case, and they do not want to invest time in it. So we had to be a little bit creative to actually find a way to stop the tester. What we are doing here is that we are retrieving the window of the tester, and thanks to a Windows API call, we simulate that you click on the panel close button. So this way it stops the loop, and right after that we can close the panel. So now with the TestStandifier, you've got two new functionalities that are exposed into TestStand, is that you can launch a tester from your sequence, but you can also stop the tester from your sequence. Quick note about using the tester into your sequence. You might have noticed that when you create a new event into your DQMH module, that you have broadcast, request and reply. But there is also a less known citizen that is run trip. And I don't know if you know what a run trip is, but actually a run trip is a request and reply and also a broadcast of the reply. For every module I create and that I know that will be used into testing, I create run trips. Why? Because I will want to use my tester to see exactly what's going on into my main VI. I told you before, if you add a breakpoint into your sequence and you press F8 to enter into your VI, in a traditional test and programming, you will see actually the code that will be performed. With DQMH, what you will see is a request, actually, which doesn't give you much more information of what's going on when the request will actually be sent to your module. So diving into your code from your sequence does not give you any clue of what happens into your module. So you need the tester for that. But if you do a request and reply, you do not see anything on the status control of your tester. So you have a window, but the window is not showing anything. You need a broadcast for that. And if you create a run trip, actually the DQMH scripters will add that broadcast for free for you. So here is a quick advice is that if you plan to use a tester from your sequence, transform your request and reply into run trips, and you will have much more information coming for free into your tester. And thanks to the APIs of the first to the two wrappers we create to start and stop the tester, it will be really much more proficient to use the tester from your sequence. Stop it, launch it and stop it and see what's going on into your DQMH module. So once we've done the source distribution and we applied the modification on the source distribution into your module, we want to create a pack library. So for test end users, there are actually two schools, old school and new school. Old school will keep all the LVIs alone into single files, all into a single folder, and you will end up at the end of your project with 1,000 of VIs all into a single folder. This is the old school way. Or we can build a PPL. So instead of having 100 of VIs, you only have one file, and all the VIs you need are inside the PPL. So we create the PPL from the module in the module modified in the source distribution. And we enforce all the dependencies of your DQMH module to be present into the PPL. So the PPL created by the TestStandifier may be a little bit bigger than the PPL that you would be creating yourself, but it makes the PPL all autonomous. So it won't have any other dependencies or on any other toolkits that may be installed, for example, on your computer. And so this allows to handle only one file. So actually, the PPL is a way for us to assemble the puzzles that is a DQMH module and transform it into a single file that you can call actually from testing. But you will see that you will not be calling the PPL itself. So this is only a way to glue all together into only one single file. For those who are interested into building things automatically, actually NI has a set of libraries that targets the application builder. These libraries are well hidden. So there are some references on the internet, so you can find these libraries. And all these libraries are well made because they are not documented at all. So if you want to use them, it's trial and error. You just throw that onto your VIs and try to understand how it works, and it will eventually build things correctly. So this seems quite simple, but the process of building the PPL correctly was quite a long run, actually. And so once we have a PPL, we could have stopped here. Oops, sorry. We could have stopped here, but we go a little bit further. We actually create a sequence file on top of your PPL. Why? Because at the end, what we want is that you use TestStand with TestStand standard tools. And so instead of having to load every single VIs from the PPL and find the exact good VI to call, we decided to create a sequence file that will be seen as a library file from the TestStand point of view. So we create subsequences to actually launch a module. So you will have a launch module subsequence into your sequence. You will have a launch tester. You will have a subsequence to stop the tester. You will have subsequence to stop the module, and you will have one subsequence per request and reply. And if you remember well, I told you before that using DQMH module in TestStand, you will have to figure out where to handle the error. It's not an easy task, actually. It will depend on your specific module, but I hardly believe that most of the errors should be handled in TestStand, actually. So what I want from my sequence file is to have at least a placeholder where I can handle all the errors that a module might return to me. So we had specifically a post-step runtime error callback inside the sequence file. This way, you have a placeholder already in TestStand to handle all your errors. So no excuse not to do it. It's all done for free by the TestStandifier. And very importantly, we also map all VI IOs to sequence IOs. So when you have a request and reply, you've got some inputs into your LabVIEW VI, and you've got outputs from your LabVIEW VI. We map all that onto parameters into your subsequence. Inputs are linked to parameters by value, and outputs are linked to parameters by reference. So at the end, you have a sequence with a bunch of subsequences that you can call, and the subsequences in TestStand actually just expose the parameters you need. And you can see what is an input and what is an output just looking at the type of parameter you have. Actually, so if it's by reference, it's an output. If it's by value, it's an input. All that is done automatically up to version 1.3 and further of the TestStandifier. We even handle enums. So enums are a specific type, and they are very useful. And so we do special things to actually create enums into the sequence file and map the enums onto the VIIO. And this way you will have enums directly into TestStand. So what does it look like, actually? So what we have on the right is a sequence that is created by the TestStandifier. And if you want to actually launch a sequence, you've got that start module subsequence. Sorry. You have that subsequence start module on the top right that you could just drag and drop into your main sequence. What we do inside, automatically we call the start module VI and synchronize module events, and we automatically link them together inside that subsequence so that you can start and sync directly from your sequence. So all that job to launch actually a module, it's all done by the TestStandifier for you. You don't have to care about it. You just call a launch module and it will actually do synchronization right for you. I told you before about the synchronization of the module ID and the test socket index. We actually modify the way the module ID is generated within your clonable module. So by default, it's only a feedback node. And I told you before, you may have some problems of cache, or you may have some test sockets that are launched before some others. So you might have some problems linking the module ID and the test socket index. We actually, by scripting, change the way the module ID is generated, and you can enforce, that's annoying. And we can enforce from testing to actually use the default module ID that the module will generate, or you can force it from testing. And if you force it from testing, now you can set your test socket index to be the module ID of your clonable module. This way, the module ID of your clonable module will always be linked to your test socket index. So if you want to talk to a specific clone from a sequence, you just have to use the test socket index, which is something that we use often as TestStand developers, to target the module actually talking to the hardware for your specific test socket. So this is done also automatically by the scripter, and you just have one parameter to fill from your sequence to decide which mechanism you want to use. And you don't have to create a dictionary, for example, on the side to link a test socket index to a module ID. So it's only a question of parameter now. And so the output, what you get from the TestStandifier when the TestStandifier modifies the module. You get a PPL, I told you before. Anyway. And you get a sequence file, so definitely that is your output. The PPL, keep it. You can use it by yourself if you want, but as a TestStand developer, you should only use what's inside the sequence. The sequence is actually now your library. It's now your module. And you've got a subsequence to actually target every request and reply that is into your module. You also have that sequence with the error callback to handle the errors directly from testing. And you have all the settings from the subsequence parameters to actually set your module and pass data or get data from it. So from a TestStand point of view, I don't know if you have TestStand developers that are not LabVIEW developers actually into your teams, but if you give a sequence to them, they don't have to care about any LabVIEW adapter or what kind of VI or which VI they should call, etc. They only work from a sequence. You now have a bunch of sequences that are related to your modules, and you have a library into testing, a library of sequences. So you can concentrate on testing. If you have some different modes into your UI, maybe you have an operator mode and technician mode into your UI, you may want the technician to see the tester. So now you can automate that. You can just call your tester launcher and stop tester subsequence to automatically launch your tester and stop the tester at the end when the technician is actually using, for example, your sequence. One thing not to forget, and this is really important, your code, the code that is actually performing calculation or controlling your hardware, is actually running in parallel to your sequence execution into the module main VI, which is a drastic change compared to traditional TestStand programming. So use and abuse of the tester. In that case, it's the only window you have on the code running in parallel to your sequence. And so my last advice is use it. It's available for free on VIPM. So there is no limitations, actually. So you can just download it and try it onto your module. It's risk-free, actually, because as I said before, we do not modify your module. We modify a copy of your module, so you won't break anything onto your existing modules. There is a forum if you have some issues. So don't hesitate to post your issues in the forum, and we'll try to respond as fast as possible. We are open to sponsorship to add functionalities. There are a few things on the roadmap, and actually it's a tool that we use for our own projects. So we develop it and we add some more functionalities when we have time and based on our project. So if we are too slow, we are actually open to sponsorship to speed up the development of the tool. And we at Neosoft ensure that it's compatible with the new version of DQMH. So if you follow DQMH closely, you've seen that lately DQMH 7 is available. And so we transitioned from DQMH 6 to DQMH 7 a few weeks after it was available, actually. So we do this, and we publish update regularly. Before the question, if you have just some acknowledgements, I just want to thank actually the two developers that are actually contributing to the development of the tool, Duyong and Rafael. They are not present today, but they spend a good amount of time on it. It's all VI scripting behind the scene. It's not easy, actually. The DQMH consortium also, because we had many questions and they always answered in a rapid manner to all the questions we had. Darren Nattinger for all the advice on VI scripting. VI scripting is really intense in that tool. And so Darren was really a useful resource for that. And I want to thank also VI Shot for sponsoring. Michael is here. And so he needed some more functionalities that was available into the tool, and he accepted to sponsor us so we could spend some more time to enrich the tool. So we are always open to sponsorship of that, and so thank you, VI for this. And it's the end of the presentation. Do you have any questions? No question. It was all clear. All good. So thank you, everyone.